Features of designing a RAS fry farm. Let's talk about what a RAS farm actually looks like. That is, how it is designed. Essentially, of course, in our northern Russian climate, any RAS farm requires an insulated building, meaning a hangar where the equipment is located. It has to operate year-round. The engineering systems include electricity supply, heating, ventilation, and sometimes air conditioning. But, as they say, the building itself isn't the most important thing. That's why it's important to look at what is so special about the technology and how a RAS fry farm should be designed. So let's go inside the production area together. Welcome! Alright, let's go. We'll begin our journey by starting from the most logical and sensible place in the entire facility, the incubation room, where everything truly begins. Because, well, fertilized eggs are what arrive at the fry farm naturally. And this is the room where they're placed. This room houses the incubators. First of all, the number of incubators needs to be calculated based on the amount of eggs you plan to place. For example, if you need to raise 500,000 fry, we need to understand what the expected loss from eggs to fry will be. Let's say we estimate a 30% loss. This means we divide 500,000 by 0.7 and get 714,000. I would add a margin for safety. So we need to place 800,000 eggs in the incubators. The first important point is to calculate the incubator's capacity. The second point is the type of incubators. There are universal incubators that are suitable for all major fish species. This is a Weiss incubator. It's a kind of flask, elongated, conical at the bottom, with water supplied to the Weiss flask from below. The eggs are constantly kept in suspension, and this is how they are incubated. It is used to incubate sturgeon, trout, African catfish, whitefish, carp, basically anything you want. But a universal incubator, like many universal things in our world, take all-season tires, for example, is not always optimal. That's why often if a farm specializes in a particular species of fish, there are specialized incubators designed specifically for that species. For instance, right now we are at a trout fry farm. Here, vertical incubators are used. So these are the incubators like this. Each one has 8 trays. These are the trays. There are no eggs here right now, so I can take them out. There's a frame inside. The eggs are placed under the frame. Water is supplied from below, rising in an upward flow here inside this frame, and in fact, from the top frame, the water falls down, 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 down. This way, compactness is achieved. According to the specifications, this incubator can hold 80,000 eggs, but in practice, based on experience, 60,000 are actually placed. So that's 60,000 in each apparatus. There are 5 here and 4 more, 9 in total. 6 times 9 is 540,000 eggs that can be placed in these devices. The water consumption for this apparatus is up to 1 cubic meter per hour. The normal consumption is a little over half a cubic meter, which is standard. As the eggs get used to it, the water consumption increases. This is how the vertical incubator is used for trout. There are also horizontal tray incubators, which are used for trout as well as African catfish. These are very good incubators, but they take up a lot of space. They are horizontal like this. So, one tray incubator takes up as much space as the 5 vertical ones standing here now. But on the other hand, it's easy and convenient to monitor the eggs. Fish farmers who are, let's say, traditionalists really like them. Sturgeon are incubated in a special incubator called sturgeon. It's very convenient for sturgeon species. Well, for all types of sturgeon fish. African catfish and whitefish are incubated in Weiss incubators. Carp and herbivorous fish are often incubated in large Amur incubators. The second important point, after calculating the quantity, you need to choose the right type of incubator. The incubator's water supply system. At this particular incubation station, we have a flow-through water supply system. That is, water flows into this reservoir. In it, the water is heated, aerated, and then distributed by gravity to the incubators. But often, in order to precisely control the temperature, reduce water consumption, and lower electricity and heating costs, a recirculating aquaculture system, RAS, is installed for the incubator. That is, water from the incubator accumulates in the filtration system. Then it is purified and pumped back into the incubators. As a rule, the incubation system, the RAS incubation system, does not include a biofilter since we do not feed the fish here. Only eggs are incubated, so a biofilter is not needed. A mechanical filter is needed, usually a drum filter, pumps, and an oxygenator is also not necessary. There's no need to supply pure oxygen, temperature correction, and most importantly, degassing, that's all. So, we don't need biological filtration, and we don't need an oxygenation system. Be very careful with disinfection. We don't use ozone on incubators. We only use ultraviolet disinfection. Otherwise, you could ruin the eggs. That's what concerns the incubation unit. So, let's go over the 3 main things again. First, calculate the correct incubator size based on the quantity. Second, choose the right type. And third, select the proper water supply system. The water flow rate in the incubator is chosen based on the water consumption required for that specific incubator. It has a specification sheet. Let's say it needs 0.6 cubic meters on average, up to 1 cubic meter at maximum, so you select accordingly. There are 9 incubators here, so that's 9 cubic meters per hour. But we usually make the system a bit more powerful for RAS and install better frequency converters so that the flow can be adjusted with frequency drives. That's basically it. Now let's look at the features of designing a larval unit. It's very important for us to determine the number of trays, and in general to select the right tanks. First, they should be convenient to work with. To do this, we need to understand what the final fish weight will be. That is, if the final weight in the larval unit is usually 5, 3, 5 or 10 grams, then the most convenient thing to work with is these kinds of trays. I'm not talking about the second tier right now. The second tier is a separate topic. Here, it's more of a necessity because there wasn't enough space. Ideally, you would have these kinds of trays in a single tier. They're perfect and convenient for any fish farmer to work with the fish. Stocking density is calculated depending on the fish species and on what final weight is planned. In other words, it's calculated not for the initial stocking, but for the final weight. Holding. It's important to consider where you will hold the fish when designing the facility. In principle, you can also use these trays for holding larvae. That is, as soon as they hatch from the incubator, we first transfer them to the holding area, especially for trout. We keep them there for 2 to 3 weeks and then move them to active feeding. So basically, in these trays, the fish stay until they reach 1, 2, or 3 grams, 10 grams at most. It's not recommended to keep them any larger in these trays. After that, they should be transferred to the next section. What's important? First of all, once again, it's crucial to choose the right containers. Sometimes the larvae are placed directly into tanks. There are ITSA tanks, sometimes larger tanks, but typically the classic option is these kinds of trays. It's important to select enough of them so that all the fry, or more precisely, by the end of the rearing cycle, when they've reached their maximum biomass, have enough water volume to be properly kept. Well, for example, 500,000 fry. Let's say we use a final density of 30 kilograms per cubic meter, with each fish weighing 10 grams. So 500,000 fry would be 5 tons of 10-gram fish. With a stocking density of 30 kilograms per cubic meter, let's grab a calculator. If we divide 5 tons by 30, we need 166 cubic meters of water. That's what it takes to raise 500,000 10-gram fish. Well, that's just a random example. It's necessary to properly set this up in the personal unit, that is, in the larval trays of the drainage system. So here it is, the frame and the upper overflow. Here it's set up like this. The upper overflow is sometimes removed, and if dirt has accumulated there, it gets flushed into the sewer. Additionally, we are now installing another sewer outlet so that we can flush out the dirt with a mesh before it reaches the mesh, because dirt tends to accumulate before this frame. We need to design a collector up to the drum filter. And here it is, the drum filter itself. What is important when designing a larval unit? If we are designing for trout, as a rule, with such densities, we need to ensure 3 to 4 water exchanges per hour at minimum. This has already been established and confirmed in practice. So 3 to 4 water exchanges per hour in the larval unit are generally sufficient for the fish to feel more or less comfortable. Therefore, the drum filter and the collector, all of it must be calculated specifically for this water exchange rate. Next, the pumps. Since we are working with fry and with trout, and salmonids are very sensitive to carbon dioxide, one of the key features in designing such fry facilities is the presence of a degasser. For sturgeon, it's preferable to have one for fry, but not strictly necessary, whereas for trout, it is absolutely essential. For whitefish, it is also absolutely essential. Naturally, a biofilter. That's right. Without a biofilter, a recirculating aquaculture system simply won't work. Disinfection. Disinfection is absolutely necessary to ensure that the fry are not at risk of infection. This is the system: a contact column, an ozonator, and a pump that feeds water into this contact column. They all work together to ensure the water is continuously ozonated. An oxygenator, meaning the water is saturated with oxygen. Obviously, without an oxygenator, we wouldn't be able to maintain high stocking densities, and of course, a control system. Moreover, it should ideally provide automatic monitoring of water parameters. We need to constantly monitor them. Here is an emergency situation, any errors or accidents. We check what's happening. For some reason, the drum filter is showing an error. Probably there's a malfunction in the automation somewhere. We need to check what's going on with the drum filter. Without such a system, well, there's a risk of missing something. Even with such a system, there's still a risk. It's just lower, in fact, and so off. Here, in the larval unit, we raise the fish to 1, 2, 3, well, at a minimum about 1.5 grams before transferring them. We grow them to 10 grams and then we transfer them to the juvenile unit. Therefore, the next thing that needs to be designed in a juvenile fish farm is the juvenile unit. There, as a rule, we raise the juveniles to their final weight. So it all depends. For example, if it's a juvenile fish farm, in the larval unit, they usually grow them to 1 or 2 grams, no more, because there are a lot of fish and you don't want too many trays. In the juvenile unit, the fish are grown to their final weight. For example, that could be 10, 20, 50, or even up to 100 grams. Here it is, the juvenile unit. And here, we can already raise the fish to a larger final weight. Again, it depends on what final product the juvenile fish farm is aiming for. What is important here? Well, first of all, you can already see that the tanks are different. These are no longer trays, and we don't need to work with larvae here at all. That's why we can increase the size of the tanks. Why make them bigger? To increase the efficiency of space usage, because one of these tanks holds over 6 cubic meters. One tank contains as much water as 10 of those trays. Naturally, this is efficient, and it takes up much less space than those 10 trays. Here, since the juveniles can be larger, it's preferable to install hydrocyclones. That is, this is a device for removing coarse suspended solids. Yes, it's not mandatory, you can do without it, but it's highly recommended. So what else is there in the tank? Feeders. In fact, to be honest, they're not always used. The drainage system in the tank, the supply system, well, that's pretty clear. Regarding the water supply system in the tank, you can't see it very well here, but there's a horizontal pipe with several small holes laid underwater. This is called a flute. When we simply pour water into the tank, it's difficult to create proper circulation. But here, there's a horizontal pipe and a vertical pipe, and they swirl the water in such a way that all the dirt from the bottom gathers in the center and is then removed through this hydrocyclone. That's why we always try to do it this way, so that we have proper water hydraulics in the tank. Here it is, the flute goes in. Here's the water supply. All the pipelines, like here, can be laid under concrete or under a metal platform. Since there were basically finished floors here, this used to be a cowshed on this farm, well, we, accordingly, had to run the pipes above the floor. A couple of words about stocking densities, probably at the design stage. If we're talking specifically about trout, since this is indeed a trout farm, we usually start with a stocking density of about 10,000 individual fish per square meter. Then, as the trout continue to grow, we gradually begin to redistribute them to provide more space. At around 1 gram, we can maintain a density of 10 to 15 kilograms per cubic meter. At 10 grams, 30 to 40 kilograms per cubic meter. At 50 grams, we can go up to 50 kilograms per cubic meter. And at 200 to 300 grams, we can reach up to 80 kilograms per cubic meter. These are the standard densities. In fact, you can go higher, but I'm just using an average, a sort of hospital average density so as not to exceed too much. Pipelines in the farm need to be calculated based on water flow rates. Well, this applies to all farms, whether it's for market fish, juveniles, or whatever else. You absolutely have to calculate them based on flow rates, because if we make the pipe diameter too large, we'll get fouling, and if it's too small, the water won't flow, and the tank will overflow. That's it. Next, all the water needs to be collected at the mechanical filter, specifically a drum filter. Well, a drum filter is the most convenient option for mechanical water purification. It rotates and cleans itself automatically. After that comes the biofilter, since this is a recirculating aquaculture system. Right now, we're standing directly above the biofilter. Here we have the biomedia. I just took it out recently. This is what the biomedia looks like. Bacteria live on it. What can we say about this? The principle and approach are the same as in the larval unit. A degasser is absolutely necessary, as well as a mechanical filter and a biofilter. In the fry unit, it's preferable to have a water exchange rate of 3. 2 or 2.5 is really the bare minimum. A contact column, meaning water ozonation, is also absolutely necessary. Here is the ozonator, oxygenation. It's exactly the same type of oxygenator, just larger, as you've seen. You can use low-pressure pumps that continuously supply water to the system, and separately they supply water to the ozonation and degassing circuit, while another group of pumps supplies water to the tanks. I wouldn't recommend combining all of this together. I prefer to separate systems so that they operate independently. If the ozonation system breaks down, God forbid, or something goes wrong with it, you can stop it, fix everything, and then restart it. But when everything is supplied through a single circuit, if one thing breaks, almost everything goes out of order. Plus, I highly recommend installing bypasses. That is, all equipment should have bypasses so that if you need to take it out of the system, you can disconnect only that unit without shutting down the entire group. And of course, a control system is absolutely essential. Control, monitoring, automation, all of this should also be in place. Yes, you can do without it, but it's better and more reliable with it. Monitoring, oxygen pH, ORP, oxidation reduction potential, carbon dioxide. Now there are already sensors for ammonium and nitrogen nitrates. That's really convenient. We're planning to test them soon. The equipment should have the ability to switch to manual mode and at the very least provide emergency signals. Let's go now. I'll show you the production unit. This isn't quite standard for a juvenile fish farm because it was originally intended as a production facility. But during the process, the client realized that this is more profitable right now. There's a high demand for fry at the moment, so I decided to focus on that. Well, why not? So right now, specifically in these tanks right here, there are fish. Well, fry 10 to 15 grams and some around 100 grams. Here they are. These are the tanks. Let me show you very clearly using an empty one as an example so you can see what's what here. Look, this is the central bottom drain where the waste goes. This waste then ends up in the hydrocyclone. About 10 to 20% of the flow goes out here. The side drain handles the remaining 80%, so the rest goes out through it. In these tanks, which are still the old model, there isn't a built-in system for removing dead fish. This is very important. The bigger the tank, the less chance you have to catch dead fish with a net. This one holds 30 cubic meters. How are you supposed to catch it? That's why now we're going to add this system to these tanks as well, and in the new line we'll rebuild them to include a dead fish removal system. Over there you can see the flute. That's the water supply system. There it is. There's an opening on this side. It creates a swirl in the whole flow so that debris collects in the center. The water exchange rate in this line is 2. But honestly, for trout, I would actually make it a bit higher. But since this was originally designed for market fish, well, that's how it is. There are 5 tanks here as well. Here it is, the miracle sorter, manual, but pretty advanced. By the way, has anyone worked with a sorter like this? What are your experiences, your feedback about it if you've come across one?